Hi everybody, it's Mr. Oliver. This video will be for the solution to free response question number 2 for the Unit 3 AP Physics 1 review practice. Let's go and get started. Alright, so this question discusses a toy car rolling down this ramp and then launching off this ramp. It starts at point A and it launches at point B. It says in the problem, the toy car coasts along the curved track shown above. The car has an initial speed when it's at point A, so it's not being dropped from rest. It's already moving. Okay. Then the car leaves the track at point B with speed v at some kind of an angle theta above the horizontal. Assume that the rotational kinetic energy of the car's wheels and energy losses due to friction are both negligible. So that means this is a frictionless track. There's no rotational inertia in the wheels of the cart or anything like that. And so the first question says, suppose the toy car is released from point A. So we are gonna start with a starting from rest. And it says, after the car leaves the track and reaches the highest point in its trajectory, it will be at a different height than it was at point A. Explain why this is so. And so if you look at the problem up here, let's just kind of sketch on this diagram. Whenever this thing launches, it tells us that after it launches, it's going to fly up in the air, and the highest point in its trajectory, which is right up here at this x, that x is going to be at a lower elevation than point A. It tells us that is a statement in the problem, and we need to try to explain why that's true. So let's think about this for a second. We do know in these kind of systems that there's no friction, no air resistance or whatever, is that we do know that energy of the system remains constant. Okay, so that's a statement you do want to indicate, that the energy of the system remains constant. So we need to try to explain, it's like, okay, why do I not have the same height at that highest point, x, that I do at the start of A? All right, so let's just think about it for a second. Whenever that cart comes down that track and it launches, whenever it's flying through the air at point x, has it stopped? In other words, did that cart just stop mid-flight at x? Well, no, of course not, because anytime you see these things in real life, it's just going to keep going. It's in a projectile motion right here. At its highest point, I didn't draw it super good. It should be more like this, horizontal. At that highest point, it's moving, right? For a projectile at its highest point, it's still moving to the right. So here, it still has kinetic energy, right? And so because it has kinetic energy, that kinetic energy takes away from the beginning potential energy that it had. And so when you're up here at this highest point in flight, you can't gain as much height as you normally would have, because it is moving. So like if I said, okay, well, here's my height at A, that's where I started from, and let's say that this point right here is point X, the point of its highest trajectory. Height of A has to be greater than the height of X. And the reason why is because sum of the initial gravitational potential energy, and I'm just going to use GPE, or in other words, UG. Some of that gravitational potential energy has transferred or changed forms into kinetic energy, right? And because there's kinetic energy here, you don't have as much potential energy available, so therefore your height is going to be less, right? As kind of a side note, I was thinking about this. What if I had this track and it came down and your launch angle was straight up? And so that cart were to start up here at A, come down this track, and then launch straight up. Well, if it launched straight up, think about what would happen. It would go up to its highest point in its trajectory, and then it would stop, right? Well, because of this, all of that potential energy has now returned to its original potential energy. So if you did have some kind of a track and it launched straight up in an ideal world, that track or that little toy car would go down and launch straight up, and its height would be exactly equal to where it started from. Okay, but that's in an ideal world. Of course, we know that doesn't happen in real life because there's frictional effects, air resistance, etc. But ideally, if you launch straight up, it'd come back right back to where you started from. All right, and so this is kind of the solution for part A, I. All right, that was worth 2 points, by the way, on the rubric. Okay, now the second part of the question says determine the speed of the car when it is at its highest trajectory after leaving the track in terms of VB and theta. Explain how you arrived your answer. So let's look at it again at its highest point in its trajectory. So whenever it's up here at this highest point, that little car, okay, is moving to the right. Well, that speed at its highest point is similar to the previous problem where we had a horizontally launched projectile. You need to remember, this is important for projectiles, that the horizontal speed, we'll call it Vx, is a constant speed. It never changes. And it never changes because there's no gravity pulling it to the right. There's no air resistance pushing it back to the left. In these ideal scenarios, this is true. This horizontal velocity is constant. So how do I get that horizontal velocity? That's what they're asking for. Well, if you look at it, when you launch at some speed, VB. But that launch speed is at an angle. Here, let me draw it down here where you can see it. That launch speed, VB, is at an angle theta. So if I want to calculate that horizontal velocity, I have to calculate the horizontal component of that initial velocity. Because remember, there's a horizontal and a vertical component. Well, the horizontal component is just going to be VB cosine theta. And that value is the same as Vx. That value, VB cosine theta, never changes during the flight of that projectile. It is a constant velocity. All right, and so that's the solution for AII. This question is also worth 2 points. All right, and so lastly, the very last part, suppose the toy car is given an initial push so that it has non-zero speed at point A. And so this is kind of what it says originally, that we're going to push this car. It's already going to be moving at point A. And it says determine the speed VA, that initial speed, of the car at point A such that the highest point in its trajectory after leaving the track is the same as the highest point in A. So what they're saying is that I could give this thing enough initial push to where when it jumps this ramp, it will actually not fall short. It'll actually climb back up to its original height of A. So the idea is that this height right here at its highest point will be the same height, if I can draw it, it'll be the same height as the original height. Right? So how do we calculate this? Well, in these systems, we have to assume that the energy remains constant. Or in other words, the law of conservation of energy states that the initial energy of the system has to be equal to the final energy of the system. And using those words, and especially in an explain kind of scenario, that's what you want to do, is you want to say the initial energy of the system has to be equal to the final energy of the system. Right? And so then you look at it, it's like, okay, well, at the top of its hill right here, what kind of energy it does it have? Well, it's got some height. I'll call that HA. It's got some initial height, but it's also got some initial movement, so it's got some kinetic energy. So our initial energy types are gravitational and kinetic. I'll put a little subscript A here to indicate that we're at the beginning point. And then at the end point, it will also have some height. We'll call this end point right here H final. Call this the final position. And it will also still be moving, so it will also have kinetic energy at that point. So it'll have UG final plus K final. All right, so if you think about it, without going through and doing any kind of mathematics, if I'm at the same height at the beginning as what I ended at the end, I would have the same potential energies at the beginning and at the end. So there's no real point in going in and messing with the potential energy terms. They're just going to cancel because they have the same amount. The cart's at the same height in both places, so they'll have the same initial and final potential energies. So that leaves us with kinetic. Well, our kinetic energy at A will be 1/2 the mass of the cart times the velocity at A squared. And at the end, the final kinetic energy will be 1/2 the mass times the final velocity at the top of that arc. Well, what did we say about the top of the arc? What did we say about that velocity at the top? Because it's only moving left and right, there is no up and down motion. It's at its top, it's at its highest point in its trajectory. It's only moving horizontally. So that means at the top of this arc, on our problem, this velocity is that horizontal constant velocity. That's Vx. It hasn't changed, regardless of how fast you gave this. All right. So once it launches, you have to figure out. It's like, well, what is that horizontal velocity? Well, what was it from before? Well, it was VB cosine theta. All right, and that's really counterintuitive because you think, well, I gave it some extra energy here. How can it possibly be moving the same speed? Well, that horizontal velocity is completely independent of the vertical velocity. Yeah, VB is going to be different. We don't know what that number is, but it's still the same expression. You know, in the original scenario, maybe this was 10 meters per second. Well, maybe now in this new scenario, it's 30 meters per second because I gave it some extra speed. But algebraically, we don't know what that is. And so what I can do here is if I look at this equation, I'll substitute in VB cosine theta for VF. And so the 1/2s actually cancel, the mass actually cancels, and even the squares actually kind of cancel. And so you can come to the conclusion that V at A must be VB cosine theta. All right. So if I gave you a number for VA, let's say it was 10 meters per second, then that means that VB cosine theta would also have to be 10 meters per second. That's your solution for part B. And part B was worth 3 points because this is a 7-point question. 2, 2, and 3 is 7 points. All right, guys, I hope that helps. If you still have any questions, just email me or post it on the Google Classroom, and I'll be glad to help you out. Thanks again, and I'll see you later.